Okay, so today we're going to be talking about basics of induction. We'll explain what induction is in a second. I just want to say that if you haven't done the reading for today, logic and proof, sections 1 and 2 of chapter 17, then you should stop the video and go do the reading before you watch this video. And I also think that around about now is when this Fundamentals of Higher Mathematics book is going to become especially important. So I'd really recommend that you guys read section 5 of this book. Okay, so let's talk about the natural numbers for a second. So we're going to, just to be clear, we're going to take the natural numbers to include 0 in this discussion, as we've mostly done this class. So we will take the natural numbers to include 0. So they look like this. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, blah, blah, blah. Okay, so we have all these guys in the natural numbers. And I just want to point out, as I have several times in the class so far, that when we use something like this that's set roster notation but has these ellipses in it, that's not a real thing. So you shouldn't write it on a test, but it is a good illustration of what's going on. So that's why I put it in my lecture notes, because it's, as you can hopefully see, an illustration of what the natural numbers look like. So we shouldn't use it as a definition because it's not really clear what the pattern might be. Okay, so let's talk about the properties of the natural numbers. So what's important about n, the natural numbers, is the following. So there's a special element, first of all. We have a special element, and that's 0. So we have this special first element that's kind of starting us off. So the first element. And the second thing that's important about the natural numbers is that we have a very special function here. So there's a special function. So let's call it S, it's usually called S actually, from the natural numbers to the natural numbers. And this is defined by sending a natural number n to n plus 1. So it kind of steps through the natural numbers, maybe. And this is called S because it's usually called the successor function. Okay, so something to say about this is that sometimes in mathematics, the natural numbers are defined to be the set that has these two properties, basically. So it's the set that has a first element and a function that kind of generates from the first element all the other elements. And sometimes the natural numbers is defined somewhat differently, and it's just proven to have these two properties. So in the part of the class where we're not in lean, where we're just writing things on a piece of paper, we're going to be rather agnostic about how they're defined. We're just going to use the fact that however the natural numbers are defined, they always have these two properties. But in lean, because lean is a very specific thing where everything is defined, or well, some things are defined, the natural numbers is actually defined to be a set that has these two properties. So that's just a bit of foreshadowing. Let me write that. So we'll see in lean that n is defined by these two properties. Okay, so because n has these two properties, we get a lot of useful stuff out about n. So because n has these two properties, we have we understand basically kind of the behavior of n. And in particular, we have the principle of induction. Okay, so what does the principle of induction say? So it says that if we have a predicate P on the natural numbers, and we want to prove that P of n holds for all natural numbers, and we have to make sure that two things hold. So if we have the following two things, if P of 0 holds, and if for any n in n, if P of n holds, then P of the successor of n holds. So let's just write that as P of 1, P of n plus 1. Then we can conclude by invoking this principle of induction that P of n holds for all n. Okay, so let me write this out in the style of natural deduction, which we won't really use at all in this class, I think, but might be helpful to kind of understand what's going on. And before I do that, actually, let me reiterate the kind of philosophical difference between induction and deduction. So in deduction, we go from the general to the specific. And in induction, we generally go from the specific to the general. Okay, so this is just a kind of philosophical point. It's not very important for our class, but we just want to point it out because it maybe will make things clear what's the difference between the words induction and deduction. Okay, so in the style of natural deduction, we can write the principle of induction in the following way. So if we want to prove that for all n, P of n holds, then we need to supply two things. We need to supply, first of all, a reason why P of 0 holds, and then we have to supply the proof that P of n plus 1 holds from the assumption that P of n holds. And if we can supply these two things, first that P of 0 holds, and second this proof of P of n plus 1 from the assumption P of n, then we can go ahead and conclude that that for all n, P of n holds. Okay, so how do we use it? Let me just kind of reiterate the principle of induction, but by talking about how we use it. So if you want to prove some predicate P of n holds for all n in n, then we have to do two things if we want to use the principle of induction. Then we have to first of all show that P of 0 holds. So then we're checking off this box up here, and then we would also have to show the second part, show that for any n in n, if P of n holds, then P of n plus 1 holds. And then if we do that, we're checking off this box. And let me give these two steps some names. So this first step is generally called the base case. And so you don't have to use this phrase in a proof, but it's very common too, and it helps the reader understand where in an induction proof you are. And this part is called the inductive step. Okay, so again, You don't have to use the phrase, but it's very useful. And also another phrase that's often used is this hypothesis. So whenever you're proving P of n plus 1 holds, you're going to be assuming the hypothesis that P of n holds. And this is often called the inductive hypothesis. So if you refer to this hypothesis by the phrase inductive hypothesis, then people will be very happy because they know exactly what you're talking about. Okay, so I want to illustrate this in the following way. So maybe this is a good picture to have in your mind. So you can think of induction as trying to knock over a bunch of dominoes. So say we have a bunch of dominoes. We have a line of infinitely many dominoes, actually. And you can think of the first guy as P of 0, then P of 1, then P of 2, P of 3, 4, 5, 6, etc. So this is infinitely long. And say we're thinking of this as proving each of these PNs, but in our picture, we think of proving them as knocking over these dominoes. So the picture that we should have is that if we do two things, if we first of all knock over P of 0, so that's akin to proving P of 0 in our analogy, and if we make sure let's say if you make sure that they are spaced so that if P of n falls or is proven, then P of n plus 1 falls or is proven, then you know from experience, although you maybe haven't experienced a line of infinitely many dominoes, but in an ideal world, you could say that if you know these two things, then you know that all the dominoes will eventually fall. Okay, so this is the mental picture I think that we should have of induction. So let's do some examples. So these are all pertaining to LO9, all of these examples. So you can expect similar ones on the quizzes now. So let's consider the predicate. Maybe I can put this somewhere. Okay, so let's consider the predicate P of n to be n or n plus 1 is even. Whoops. And we want to prove that this always holds. We want to prove that P of n holds for all n in n. Okay, which should be true, seems true. Then let's look at how we would do this using induction. I think induction is really the only way that you could actually prove this. Well, maybe not. I don't know. Let's use induction to prove it anyway. So the first thing we should do, which is not strictly necessary, but it's always nice in a proof, is to tell the reader what's going on. So you can say, we're going to prove this by induction on n. So there's only one variable in our statement here, which is n, but sometimes there are more than one variable, so it's always nice to say which variable you're doing induction on. We'll see some examples with more than one variable. Okay, so we should have these two parts of the proof, not including the introduction and the conclusion that just tell the reader what's going to happen and what has happened. But in the body of the proof, there will be two main steps. So there will be the base case and the inductive step. So these should generally constitute, 2 paragraphs, unless your proof is very long. Then you could have more than 2 paragraphs. But in general, you can think that these each constitute their own paragraph. So for the base case, we want to prove P of 0. So let's write that out in words. So we want to show that P of 0 holds, which is 0, or 0 plus 1, which is 1, is even. Well, this is easy because, of course, we know that 0 is even. Okay, so we know that 0 is even, so this holds. Okay, so now we're done with the base case. We've shown that 0 or 1 is even because we know that from elementary school. Now for the inductive step, so this should always be the second part of the body of the proof. We want to suppose, well, we want to consider a natural number n, which maybe I can write that explicitly. So let's consider n and n, and suppose that P of n holds, which is that n or n plus 1 is even. So let me just say that this guy here, in lean, you would have to write this. You have to say like assume n. But in a proof like this, it's pretty clear because we're doing induction. Induction kind of always follows the same pattern that if you didn't have this little phrase, that you would, of course, be talking about a natural number n. Okay, so we're going to suppose that n or n plus 1 is even. And now we want to show that P of n plus 1 holds. So if we plug in n plus 1 for n, we're going to get n plus 1 or n plus 1 plus 1, which is n plus 2, is even. Okay, so now we want to show that n plus 1 or n plus 2 is even. Now let's look at our hypotheses. So, in lean, we can think of, if we wrote an underscore, what hypotheses are available. One is this guy, which is an or statement. So we're going to want to use, at some point, and I think at this point in the proof, or elimination or proof by cases. So we can say something to the reader about the fact that we're doing a proof by cases, but I think it's pretty clear because this proof is so short what's happening. So first, we're going to suppose that n is even, and we want to show, remember, that n plus 1 or n plus 2 is even. So in this case, we just do a little bit biggie. We say, okay, if n is even, well, is n plus 1 or n plus 2 even? Yeah, n plus 2 is even, right? Because if we add an even number and 2, we're going to get an even number. So n plus 2 is even. So of course, then n plus 1 or n plus 2 is going to be even. Okay, so in this case, n plus 2 is even. So n plus 1 or n plus 2 is, of course, even. Now, for the second part of the or elimination for the second case, we can suppose that n plus 1 is even, but now we don't have any work to do because we're trying to show that n plus 1 or n plus 2 is even, so we just have to use a tiny instance of or introduction and just say, then of course, n plus 1 or n plus 2 is even. Then we can just sum up. In any case, in either case, n plus 1 or n plus 2 is even. Okay, so we've completed the inductive step because we've shown that n plus 1 or n plus 2 is even with our hypothesis that n or n plus 1 is even. Right? And now, again, it's always nice to have a concluding paragraph. So let's say, therefore, by the principle of induction, it's always nice to invoke the principle of induction explicitly. We have shown that n or n plus 1 is even for all n and n. Okay, so what you put for this first paragraph here and the second paragraph is kind of up to you, but I would say that you have to use the word induction somewhere in the proof, just so people know what the heck is going on. Okay, so that people know that we're using induction, which is a very specific proof style. Okay, so if you have any questions about this proof, would really recommend you guys post a question about it on the discussion board. And I should have said this before when I started out proving this, but for all of these examples, I want you to pause the video after I give the statement of the exercise and try to do it on your own, though maybe it was good to see one example. So try to do it on your own before you continue the video. That's how you'll learn the most. Okay, so let's do another example. So let's prove this famous equality. So if we sum up all numbers from 0 to n, then we have this nice formula. And so note here that I is a bound variable. I don't know if we've explicitly talked about this in the context of sums, but I is a bound variable. And this equality here, we're saying holds for all natural numbers n that we might consider. So we want to prove this guy for all n and n. Okay, so now I want you to pause the video and try to do this yourself, or at least think about how you would do it, and then watch the solution which is about to come. That way you'll learn the most. Okay, so how will we prove this? So the first paragraph should be telling the reader something about what's about to happen. So just as before, I'll write, we prove this by induction on our variable n. So now there are two variables, and just to be clear, we're going to prove this. I mean, the I is bound, so wouldn't make sense to do induction on I at all, but just to be clear, we tell the reader that we're going to do it by induction on n. Okay, so now we're going to have these two paragraphs. The first one is going to be showing the base case. So for the base case, we will show that if we sum up all the numbers from 0 to 0, then we're going to get 0 times 0 plus 1 over 2. So we're just plugging in n into this thing that we're we're plugging in 0 into this thing that we're trying to show, where all the n's are. So we plug in 0, we find this. But then we think about this and we think that, okay, if we sum up all numbers from 0 to 0, that's of course 0. And 0 times 1 over 2 is of course 0. So we can just say, since both sides are 0, this clearly holds. Okay, so now we have to do the inductive step, which is always, or well, not always, but usually the harder one. So for the inductive step, we're going to consider an n and n, and we're going to suppose that if we sum up every number from 0 to n, then that equals n times n plus 1 over 2. Now we want to show that this holds. Maybe I should put an extra line here. We want to show that this holds where we plug in n plus 1 for n. So here we have an n up here, so we're going to put n plus 1, I. And now for n, we're going to put n plus 1. And here, we're going to put n plus 1 over 2. Okay, so it's a matter of style here, whether you put right here n plus 1 or n plus 2, like if you kind of just simplify automatically or not. I would say that when the formulas become complicated, like this one's starting to get a bit complicated, then it's always nice to not simplify because then the reader can more easily see where you plugged in n plus 1. But it's just up to you. We always want to be as nice to the reader though as possible, though we don't want to insult their intelligence. So it's a fine line sometimes. So now we can just do a calculation. So we're trying to show this equality. So we're going to start with the left-hand side, and we're going to observe. So we're trying to use, let me point out, so whenever we do this, we're trying to use our hypothesis somewhere, right? So we have our sum here that goes from 0 to n plus 1, and it might not work. I mean, it's going to work, but if you saw it for the first time, you might not know if it would work. But it seems like a reasonable thing to do to split up this sum so that you're not summing up altogether all the numbers from 0 to n plus 1, but first you sum up all the guys from 0 to n here, here, and then you kind of split off the last term. Because then this guy here, sorry, I'm writing so much yellow on this guy here, it does appear in our inductive hypothesis, so we can use this equality now in our calculation. Let me erase some of this yellow. Right, so that's a good strategy. You just want to try to massage the thing that you're trying to show so that you can kind of break off pieces about which you know something because of your inductive hypothesis. Okay, so we know something about this big sum. We know that it's equal to n times n plus 1 over 2 by our inductive hypothesis. And now we still have this term here. And now here we can give a justification. So here we could maybe give a justification, but it's pretty obvious because that's just how sums work. So maybe you don't want to do that. But here it's important to alert the reader to what's going on because they might read this and be like, what? Why is that true? So we can just remind them that this substitution that we've made is exactly our inductive hypothesis. Okay, now we just do a little bit of arithmetic. So how does this work? So if we multiply all this out, so we're going to get n squared plus n over 2, and then I want to get this other thing over 2. So I have this, and then I can combine all the terms. And let me also say that it's not so important to be super creative at this point because we know that our goal, let me write, so maybe there's some space here, we have to do stuff here. But we know that our goal is to show that this sum is equal to this, right? That's what we're trying to show right now. So we can just check, actually, if we multiply out these two guys, will we get this thing in the numerator there? And you can check that, yes, that this the second thing is a factorization of this first thing. So actually we can just say that they're equal. Okay, so since you know both ends of this equation, so this is where we're starting and this is where we're ending, you know like the beginning and the ending point, then you can at some point just not cheat, but you don't have to think too hard about how to factor this guy because you know what the answer hopefully is. Okay, so it's just a little tip, not to forget that you know what the answer should be. Okay, so now we've shown this equality. We've shown that this first guy here is equal to this last guy. So this whole equation here, this whole thing here, this whole thing is part of this sentence that begins, but we have that. So maybe it seems a bit weird, but we should put a period there because it's kind of part of the sentence. Okay, so now we've finished the inductive step. We've shown our equality, assuming our inductive hypothesis, and now we can just write a conclusion. So we can just write, therefore, by the principle of induction, we have that this sum is equal to n plus 1 over 2 for all natural numbers n. Okay, so that's it. Those are the two examples I want to talk about in this video. If you have any questions, like I said, please put them in the discussion board. These notes may be slightly different, but the notes that I'm using right now are on OneNote, where I usually put notes so you can see all of it together there, so you don't have to watch the video over and over again if you don't want to. And I'll see you in the next video.